So is it okay? Can you see that now?
Yes, sir. Yes, sir. You can start now.
We should start. All right. Fine.
Okay.
Good afternoon again. Today we are at the penultimate lecture on the course of high pressure physics. And as in the last several talks, we are discussing physics of shock compression. The last lecture, we left at a point. It's not responding.
Sir, click on the slides and then next button.
Okay. All right. So in the last lecture, we were discussing about if there are certain deviations or certain special features on the PV curve, it's called Hugoniot, then it may have some consequences, whether a single shock or multiple shocks will travel in the material. Specifically, we talked about this example, which had a kind of a cusp here. And in a case like this, we can see is this point, if we try to connect this point to this point, then it's not likely to avoid this point. So there is no direct chord which connects these 2 points, or any point which is between this and this. We cannot have a direct chord which starts from the ambient conditions and connects it to that. And recall that that's the path shock takes for loading itself. So the very fact that there is no direct path available between this and that implies that these two states are not relatable to a single shock. So in a case like this, what happens is there is a shock from here to here, which takes compression from here to here and the pressure here, and then a second shock, which takes this state onto a state between these two. And we discussed what are the conditions that these two shocks, which are shown here, will become one. So this is a shock 1 and this is a shock 2. Under what conditions these two shocks will merge into one? And one of the way to derive that condition is that when this shock speed becomes more than this shock speed, and then we can write down in terms of the jump conditions, this shock speed is given in terms of the jump conditions like this, and this shock speed is shock speed with respect to the material which is at rest ahead plus particle velocity. And again, using jump conditions, one can write in the form of pressures and volumes. Then what it means is if this shock speed is more than this, then this shock will overtake this. And when this becomes equal to this, it will become a single shock. So that implies that this condition, this inequality, must be satisfied for a single shock wave to connect the initial point to the final point. We can also put it directly in terms of those two states, which we showed between this, and this, that the slope between the first 2 points, that is between this and this, is less than the shock between the first 2 points is less than the slope between the last 2 points. So in that case, again, a same condition will be satisfied. So this is a simpler condition than the previous one. So implying that when the slope of the Rayleigh line from V1 to V2 becomes larger than the slope of the Rayleigh line from V0 to V1, then a single shock forms. Otherwise, the states are accessible through 2 shocks in this case, and in general through multiple shocks. And we also discussed about that how launching multiple shocks helps one gets into the state of higher compression, we will not reiterate that. We showed here one example where a single shock cannot be formed. In fact, it will give rise to two shocks. This is a condition which arises many a times when we are dealing with the materials. Here is another example. Suppose a material is undergoing a phase transformation at some pressure. This is an example of quartz. So from here to here, it is very simple. But from here, if this point we want to connect, it will not be able to connect. You can roughly see it will not be able to connect to any state which is less than this. So what will happen is, if we start from the initial material and launch a shock, which you want to take it to, let us say, somewhere at 30 GPa or 35 GPa, then it will take this material from to here as one shock, and from there to there by another shock. So the multiple distance of when you do the measurements, continuum kind, which measures the waves which are traveling in a material, when you don't see a single wave traveling, instead multiple waves traveling, that indicates that there are very specific features in the Hugoniot which it is reflecting, or vice versa. Given the fact that multiple waves exist, implies this, and if there are specific features in the Hugoniot, it will show in the form of the multiple waves. This is a general thing, and we will discuss a few more features where this becomes very important. And before we go into certain other examples where the form of the Rankine-Hugoniot curve has implications on how many shocks will be launched in a material, we will, for the sake of completion, also mention the differential form of the conservation laws. Recall that when we deduced the conservation laws of mass, momentum, and energy earlier, we presumed a very simple geometry, the planar geometry. That is, the space is divided into two parts. One, below a particular plane, it is all under shock, and above a particular plane, material is not shocked, or vice versa. So it was very simple geometry, and we could deduce, we deduced jump conditions based on that. But as you know, the fundamental laws of physics generally are stated in terms of the differential equations. And the reason is that there could be the situations which may vary as a function of space and time. So it's important to know how those conservation laws look when one wants to see that in the differential form. I would state those here without proof. And of course, if you see some of the references which I mentioned right in the first lecture, you can deduce some of the deductions of these differential forms. But for now, we will not discuss about the derivations of this. So let us see. The mass conservation is stated like this: that the rate change of the density is a function of time at a constant x plus this is specific density, that's inverse of volume, specific density multiplied by du dx, the gradient of the particle velocity as it travels at a given time, plus particle velocity into the gradient of the density at a given time, it has to be equal to 0. Recall, a total differential can be written like this: d by dt of x is equal to the partial derivative with respect to t time at x, and this term u into dx with dt. If you use this equation, can be written in a very simple form, which is this: total derivative of the density with time plus density into derivative or gradient of particle velocity with x at a given time has to be equal to 0. One can, for example, presume that if there is no time dependence, then this rho u has to be constant, and from there one can deduce the kind of the mass conservation form that we discussed earlier. The momentum conservation, this you can see is density into rate change of the particle velocity with time, then density into particle velocity and the gradient of particle velocity at a given time, and the partial of pressure with x. So this is representative of some kind of a force. And again, using total derivative, relation of the total derivative with the partial derivatives, that's d by dt, very similar to what we mentioned in the previous projection as this. This momentum conservation equation can be written in a very simple form, that is pressure density into du dt plus partial derivative of pressure with x. This has to be equal to 0. Likewise, energy conservation can be written in terms of recall. This is energy, internal energy, plus u square by 2 in a sense representative of kinetic term. The total derivative of that times the density, then this term and the total derivative of the density with respect to time, and then there is a term which is a gradient of particle velocity and a gradient of pressure, and pressure into gradient of particle velocity is equal to 0. So this is the term of energy conservation, and as I stated earlier, if one presume appropriate boundary conditions of the kind that we deduced, in terms of which we deduced earlier conservation forms or jump conditions, one can, from these equations, deduce those forms. We restate that the derivations of jump conditions, as we discussed earlier, the derivations of the jump conditions assume absence of any external source of energy. That's why right in the beginning we stated that we are talking about non-reactor materials. In case a material reacts, and that means there is an energy source, and then obviously some of these jump conditions, conservation laws, won't in general be applicable in the form that we stated. So in addition, viscous energy losses, you see, when a shock wave is traveling, as we discussed, it is carrying certain mass, dragging certain mass, as we say, with the particle velocity. So it should have certain viscous losses. And again, as the shock state is a state of higher temperature. We talked in the last lecture that along the shock path, the entropy increases and the temperature increases. So as the shock state is a state of high temperature, and the material head is not, so there will be a heat conduction between these two. But however, these two losses are rather small. It's basically because the heat conduction is a slower process compared to the wave propagation. And viscous force or flow is usually small, as its magnitude depends on rate change of stress. We should also state that the differential conservation equations mentioned in this and the previous projection are not valid across the shock front because that represents a discontinuity in compression. So obviously, then the differential will diverge at the shock front. When one is solving certain shock wave problems in terms of the computer codes, which are based on the hydrodynamics, which employs some of these differential forms of conservation laws, one requires an additional term representing viscosity. That's that term, which is rather small. That small viscosity actually acts to spread the shock front over a short time interval. so that the discontinuities are avoided in some of those calculations. This is, in fact, the concept of virtual or small viscosity into these equations was realized way back when the field started and was introduced by Newman in late or early 40s. Now we come back to again the implications of the phenomena which take place in the material. We talked about that in case there is a phase transition, a single wave will not travel. Now, I recall that Dr. Pandey, in one of his talks, discussed about that beyond a certain magnitude of deviatoric strain or stresses, material undergoes a plastic flow. So, so far we have been talking about, in a sense, fluids. We did not talk about the deviatoric stresses and so on. But when we refer to the solids, that condition is bound to arise, that we have the pressure or the stresses are no more means pressure. It is, in fact, directional. So along the shock direction, the stress, as we should say, is more than the transverse direction. So we would say longitudinal stress is more than the transverse stress. So that means there is the moment the shock is launched in a solid, there is a deviatoric stress, which is a difference in a broader sense, which is a difference between longitudinal stress and the transverse stress. And obviously, that difference cannot be allowed to grow indefinitely. The moment that difference, the stresses that a material can sustain, goes beyond a certain threshold value, often called the strength of the material undergoes a plastic deformation. And when the plastic deformation happens, the deviatoric stresses, or the difference of the stresses between the longitudinal and the transverse, cannot be sustained, it falls. So there are signatures of that phenomena when one studies the shock wave propagation in the material. Specifically, what is going to happen, I'm shown here. This is a PU diagram, if you recall. The PU diagram of an elastic material, for example, is this, shown extended by a dotted line, which is this. But in reality, beyond a certain threshold value, which we call Hugoniot elastic value, beyond this does not extend. It actually deviates from this particular value. So the PU curve starts in the case of plastic flow starts showing a feature like this. It increases elastically to a value and then it takes a different. So we will call that equilibrium plastic Hugoniot. In contrast, we call this as instantaneous elastic Hugoniot. Now think of a material making an impact on another material. Let us say in this case what is shown here is sapphire. Sapphire, the elastic limit of sapphire is quite high. Suppose we have a copper or any other material making an impact on this. What is going to happen is the moment the impact takes place, that particular moment, infinitesimal small difference in time, it is going to go into this unstable state because it has not yet realized that how much of stress deviator exists. So instantaneous value of pressure that it is going to have or stress that it is going to have is an intersection of this, which I call as metastable extension of PU curve with this. So this is the value it is going to achieve. And after a while, when the material that realizes that there are large deviatoric stresses, this will start relaxing back slowly, and it will come to the equilibrium value, which is this. So the experiment as a function of time, if you see, you would see a kind of a time evolution. Let me rephrase. At the impact surface, the material is shocked to a state on the instantaneous elastic Fubunio. This is due to the fact that material takes some time for the elastic plastic transition. The instantaneous state represents obviously a metastable state, and therefore is a state of higher energy, and it must evolve to the equilibrium. So the transition from a metastable elastic state to plastic equilibrium Houguenot is studied by measuring the profiles, the shock profiles at the back end of the sample of different thicknesses. So you will do experiments with the sample which is thinner and then thicker and so on and so forth. And this is how it looks like. Suppose you do experiments with a very thin sample, what you're going to see is a large jump here, which we showed as instantaneous metastable state. Then it is going to relax back and eventually slowly going to go into its equilibrium value. Okay. If we took a thicker plate, this relaxation won't be that much, so it will go and slightly relax and then. And if you have a still more thicker plates, it will go to what we call as the stable equilibrium phase. So this is the first jump it will take, and this is the final state it will occupy. Okay. So this represents that Houguenot elastic limit, and this is and then this is the final transition stress. It will take this. Okay. So shock waves in a very thin plate will have elastic and plastic shocks higher than the equilibrium elastic and plastic states. For thicker samples, these are smaller than those of thinner samples. And for sufficiently thick samples, these shocks represent the equilibrium value. And incidentally, this decay as a function of time, if you want to study, one requires material modeling, that how that instantaneous metastable state evolves. So one has to see what exactly happens under the plastic deformation and so on. So there are models, we will not talk about it. Now, still more complicated situation or a complex situation could be that a material has a phase transition in addition to the elastic plastic transition. This is an example of iron. You know, we in the very first lecture we talked about iron, where phase transition was detected with the help of the shock compression. So in a case like this, you see that this is a first metastable curve of the iron representing its initial BCC phase. And so elastically, if it stayed elastic, this is how the dotted curve will be loading the shock wave. And actually, beyond a yield point or a Houguenot elastic limit as it is called, it will take this curve. But before it completes this, it's undergone a phase transformation. So there's a transition point, and instead of this dotted curve, it takes this curve. So this is also a metastable state because plastic deformation precedes the transition, but phase transition does not let it persist forever. And the moment there is a phase transition, it evolves into this PU curve. And so this is the kind of stable PU curve, equilibrium PU curve of iron. So let us say if an iron was impacting an aluminum plate, okay, incidentally, aluminum other than HEL doesn't show any other phase transformations. So suppose one is doing that experiment, either aluminum or let us say sapphire, it makes an impact. Then you expect that it should have it should represent a metastable state where it intersects this elastic Houguenot with the target with the impacting material, and then another metastable state, which is essentially extension of this plastic deformed state, And then finally the one which it should have, which is the transition after the transition. So you expect that if an iron makes an impact and you study the shock wave propagation, you're likely to see three waves. So as I said, A and B represent the states that will be reached near the impact boundary if the elastic plastic transition is faster than the structural transition. If incidentally, if structural transition is faster than this obviously won't, then the sequence will change. So the C represents the equilibrium state of this is incidentally the HCP phase at high pressure. So it represents the hexagonal closed back Hugoniot for iron when impacted by the fire plate. And this is how the shock wave will look like. This is for a thinner plate. You would see that you would have a shock here and then another here, and this is the final equilibrium value that it will have. So this is the kind of equilibrium elastic limit, which we call Hugoniot elastic limit, and this is then the plastic shock. Okay, and then it takes the value that was expected it to take, and then it undergoes in that plastic state another phase transition, and then it takes it to its final equilibrium value. So this is how the shock wave will look like if you study the impact of iron with another material and see the propagation of the shock. Incidentally, the time evolution of the waves, such as this, where it is representing the phase transition, has information about the kinetics, but then again, it requires very detailed modeling to deduce any information from this. Now, what we discussed so far is that if one makes what one calls as continuum measurements of shock wave propagation, particle velocity, shock velocity, and so on, there is a certain amount of information that can be deduced by studying this continuum behavior. And we discussed also in the last lecture, the whole purpose of studying the shock wave physics is to try to understand thermodynamics of a material, what constitutes the material, what are the various contributions at a fundamental level which decide shock wave propagation and so on. And in principle, that whole process, that whole calculation or whole prediction of this shock wave propagation can be reduced if we have complete information of what one may call as complete equation of state. Now, let us now talk about an example of an equation of state, which is not complete, as we'll see, but it is very commonly used. It's called Mie-Gruneisen equation of state. But before we talk about specifically about, there are certain general comments about the equation of state. For finding an equation of state of a material, one needs to know Helmholtz free energy from which various variables can be calculated. Some of these things we also discussed during last lecture. A typical solid material comprises of electronic states and the vibrational states. And if you recall, Dr. Postwal talked when he was talking about first principles methods, we discussed that the electron states and the vibrational states in some ways can be computationally separated out in terms of the Born, Oppenheim, and approximation. You can treat them separately. In the sense that the vibrational states, the electronic energy introduces itself as a potential, and for electron states, freeze the atomic positions, you don't let them vibrate. It's basically because the vibrational motion is very slow compared to the electron motion. Basically because the mass of an atom is much higher than that of an electron. So these two features of these two aspects of the material or components of material physics can be separated out. That electron states can be calculated separately and the vibrational states can be calculated separately. Let's now talk about the vibrational states. For those of you who have been doing work in the matter physics, know that in all materials, atoms incessantly oscillate around their main positions. And this vibratory motion can be described by introducing a set of coordinates that are linear combinations of the particle displacement coordinates. And those linear combinations of particle displacements have to be such that they are independent of each other and are called normal modes. So the whole treatment of vibrational motions of a solid is cast in terms of the normal modes, which are 3 times the number of particles. So one can solve vibrational states for the vibrational states of a solid using various codes and so on. Now let us say that we know the vibrational states, then the partition function can be written like the Dj represents the vibrational state, and if you call this is Li plus half into h mu. So this represents occupancy of a vibrational state characterized by the frequency ui. So then in that case, one can write down z in terms of all this. So then free energy can be related to z in terms of minus kt log z. Incidentally, all this is standard treatise and it's discussed in Born and Fong dynamical theory of lattice. One can master this for those of you who are not exposed to this. For a single oscillator, that contribution from each of that oscillator to the free energy can be written in h mu by 2, which is the 0.2 to 0 point motion, and this is the occupancy of various states. And then the total energy, total free energy can be written phi, which is a contribution coming from the electron states, plus sum of all phi's, which is the sum of all the vibrational states. So it's phi plus these terms sum up overall vibrational states. So phi is generally called cold energy contribution and represents electronic states. In principle, at very high temperature, this would also have temperature contribution. Okay? That one has to invoke temperature dependent Fermi-Dirac distribution of the electron states to take care of the temperature. But generally at not very high temperatures, that contribution is rather small and can be ignored. So the dominant contribution to the temperature is essentially coming from the vibrational motion, and it's right here. So the energy can be written in terms of F plus Ts minus F plus Ts. So it's equal to F minus, the entropy can be written like that. Incidentally, recall that the pressure is a volume derivative of F as if at a given T. Now, starting from this, one can work out more details of all derivatives and so on. That bookkeeping we are not going to show here. So the total energy can be written like this, where specific heat at a constant volume is a derivative of energy with respect to the temperature at a constant volume. I take this shock as you find the temperature derivative, partial derivative of these terms. Then at very high temperature, and Kt is much larger than h nu, this term can really be replaced like this. So this takes more or less a constant value times temperature. This is I think Dulong-Pettit limit of the Dulong-Pettit limit of specific heat. So then one can write down pressure. The pressure is a derivative of F with respect to V. One can find that derivative, and then the pressure is like this. So it has a term which is derivative of the electronic energy with volume, and then it also has the terms which are coming from the vibrational part, which are these. Now let us define what is called as Grunneisen parameter. The Grunneisen parameter is a logarithmic derivative of the vibrational frequencies with volume, or minus of that. It can be written as minus V of ui and the derivative of mu I with volume. So it represents how the frequencies change as you compress a material. So then the pressure can be written if you remove this definition of the gamma I. Then the pressure can be written here, which is minus d5dV plus sum over gamma I for each vibrational state. So you sum it up over all this. And so indirectly like this. So this is a complete form into which one solves vibrational frequencies exactly. You can substitute to this and calculate the pressure. Because in general, the calculation of dynamics of solids, so the vibrational frequencies of solids is rather complex and a very time-consuming process if you have to calculate at each volume. Many a times, some simplifications are introduced, and to get a feel of how these terms have the relative values, or what kind of relative values these have, one introduces a certain approximation Einstein model, which has only one frequency for all modes. So in that case, all gamma i's are equal, or the Debye approximation, where the frequency changes as a function of wave number linearly, and so it has an upper cutoff frequency. So accordingly, one can evaluate these terms. So if we, let us say, take an Einstein model into which all gamma I are equal, then this takes a form which is this, which is minus d5dV plus gamma by V into E vibration. So indirectly, this is equal to, this is a cold contribution to the pressure, which is essentially because of the electronic states, which is temperature independent, plus gamma by V and E minus E0. This is called Mini-Grunneisen equation of state. We discussed here quantum statistical physics behind the Grunneisen equation of state, a more heuristic derivation which does not require discussion about vibrations in the sense we talked about. One can refer to this paper by Johnson. One can also talk about Grunneisen parameter or Grunneisen approximation in terms of the thermodynamic treatment. So in a broader thermodynamic treatment, one defines gamma as a derivative of pressure with energy, or inverse of derivative of energy with pressure, one by of that. So this is the definition of this. So gamma, if gamma depends only on volume, which basically means in terms of the vibrations that they are invoking quasi-harmonic approximation. That is, there are no and harmonic interactions material. Then if the gamma depends only on volume, then the defining equation, that is this, can be integrated, and one can write on pressure in terms of E minus E naught. Just a simple integration of this. And as we said in Einstein model, if all gamma i's are equal, then at temperature T is equal to 0. This equation is same as what we showed in the last video. With reference to the ambient conditions, one can write down this P is equal to P naught gamma by V E star plus E ambient minus E zero, where E star represents energy with respect to the ambient state. So this is the difference between the total energy and the ambient state. So can write on this P is equal to gamma by V into E star plus this P naught, which is cold contribution, plus this. The blue part is only a function of volume. It has no temperature dependence in this. So pressure then can be written like this. A large amount of work in on the theoretical side to understand shock wave compression has been to evaluate how to evaluate gamma or Gronissen parameter under various thermodynamic conditions. For those of you who want to know more details about this, I refer the article by my colleagues, Dr. Dodwal, Jessica, and Dr. Stamdam, written way back in 1983, extensive review of this subject in Journal of Aviation State. Now, we will stop discussing more about thermodynamics of the shock wave propagation, and now talk here a little bit about what are the kind of the measurements which are done under shock wave. What, for example, we kept on referring to shock speed and particle velocity and so on. So how are typically these measured? So this is one of the geometry which is adopted to measure the shock velocity. That this is the material, let us say we want to study, which is a driver plate comes and makes an impact. This is a material which we want to study the shock propagation in. Then what we have is that we will embed a PZT, which is a piezoelectric pin, on driver plate, and another one on the sample. We know exactly how much is the thickness of this. We begin the experiment. Before we begin the experiment, we very precisely measure the thickness of this material as well as of this material, though that's not really relevant here. So as another plate comes and makes an impact on this, and the shock wave reaches the back end of this, the piezoelectric crystal, which is embedded at the end of a cylindrical metal rod, electrode, gets shorted, or the outer boundary gets shorted. Incidentally, the PZT or the piezoelectric crystal is installed, is put in here in this rod and a pin, and is insulated from the outer boundary, which is grounded. So the moment the shock wave comes and makes an impact on or reaches or makes a contact with the piezoelectric crystal, it generates a pulse. So we know what is time t is equal to 0 when the shock wave has reached here, presented here. So that's time t is equal to 0. And as this shock travels in this, it reaches a second pin. And again, that piezoelectric crystal sends a signal the moment the shock wave makes contact with this. So that when the shock wave arrives here, it generates a second pulse. So we know the time difference between these two, and we know how much this distance is. So one can calculate exactly how much the shock's velocity is. Incidentally, this can also be measured these days with a stick camera, because once the shock wave reaches at the free surface of a material, it degrades its reflectivity. So by measuring, let us say, when it reaches here and then it reaches here, one can deduce what is the shock velocity. Particle velocity also likewise can be measured by using some gauge. Earlier days, what was widely used was called electromagnetic gauge, where electromagnetic wire or a foil was embedded into the material, and then it was put under a constant magnetic field. And when material moved, that gauge moved in the magnetic field, it generated electromotive force. That EMF was measured and was related to the particle velocity. Now, this is not very widely used. However, a lot of work has been done on this, and there are several reports on this in the various national labs archives of US, Los Alamos, as well as Lawrence Livermore. We will not discuss much about it now because it is more or less out of vogue now. What is widely used now are interferometric techniques, specifically VISR, as it is called, which is an acronym for Velocity Interferometer System for Any Reflector, and VISR, which was first developed by Barker and Hollenbeck way back in 1975. And it's based on a principle that it measures the velocity of a sample surface at an interface between an optical window material set against the sample. We will very shortly show an example of that. So basically, let us say if this is a reflector, it's a laser beam which comes here, it reflects off this. It is split into two parts. One part is sent into a delay, say through at a long. Another part just travels here, and one studies the beats between these two, and the beats of these two reflect if there is a change in the velocity during the period that the delay has caused. So using this, one can deduce the, 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 the particle velocity at the interface of the object that we are interested in. For more details, one can refer to these articles. There are incidentally, other than VISR, there's also Doppler shift method which is used, and there's also another one which is based on heterodyne, which is again based on the interferometric principles. So these papers, these three papers, discuss various details about this. Let's now come back to from where we started. Recall, in the first projection itself, we said a shock wave, a one-dimensional shock wave, as it's launched into a material, brings about a uniaxial compressive strain. That is, if this was, let us say, unit cell, it will compress it like this. It will compress more along it, but will not expand it in other direction. So only uniaxial compression will take place in this direction. It will result in, as I discussed a few minutes back, it will bring about the deviatoric stresses, and it will have its own consequences because a material will not be able to sustain deviatoric stresses beyond a particular value. So therefore, the uniaxial strain state cannot be indefinitely retained. Questions have been asked whether uniaxial strain state exists at all. And the reason it was doubted was way back in 70s, experiments by Winton Johnson, Mitchell, and Keeler and Evans showed through the flash XRD studies on lithium fluoride, shock to 12 GPa, and they found that the material only showed hydrostatic compression, which means that there is no uniaxial compression in this material. So lots of discussion took place subsequent to that, and if it is a hydrostatic, how how a material evolves from uniaxial strain state to the hydrostatic state and so on. And a lot of theoretical work has gone into studies of this. It required invocation of variety of kind of defects which contribute to the plastic deformation. And incidentally, the plastic deformation is the key to the whole rationalization, that the plastic deformation takes away the deviatoric stresses and therefore relaxes the local strain from uniaxial to the hydrostatic. Having said this, the geometric conditions of the material require that the macroscopic strain is still uniaxial. Now, microscopically, it has become hydrostatic. Macroscopically, it is still uniaxial. In recent years, more careful experiments have helped understand how the whole thing takes place. For example, in lithium fluoride, single crystal, along 111, the Hugoniot elastic limit is about 4 GPa. So one expects that up to 4 GPa, the expected microscopic strain will be uniaxial. Okay? And indeed, XRD experiments showed no transverse deformation, implying or confirming uniaxial strain. In contrast, if the experiments were done with 100 direction, then HEL beyond H, specifically beyond HEL value, then one would expect macroscopic elastic plastic deformation, and the XRD measurements really showed that. And the macroscopic state of strain, microscopic state of strain found with for the shock along lithium fluoride 100 direction beyond HEL to be hydrostatic. More details, for more details, one can refer to these. So in addition to the experiments which people have been doing, which are continuum measurements, study of the shock wave propagation of the materials, in recent years, there have been significant addition to the experimental measurements. Earlier studies were mostly continuum in nature. Specifically, some of the work which required one to confirm whether insulator to metal transitions take place in a material under shock compression. Electrical conduction measurements were developed, and celebrated paper is studies on metallization of hydrogen by Nellis and colleagues. So one can measure the electrical conduction as a function of shock compression. Subsequently, lots of other physical measurements became possible. For example, absorption measurements, material under shock compression, or reflection measurements is a function of compression, or luminescence measurements under shock compression. An example of this I was personally involved in was ruby luminescence or ruby fluorescence, which is also the pressure marker, and it studies under shock compression. So various investigations for absorption, Neil Holmes and people, colleagues worked on this. Incidentally, Raman, I forgot to mention here, Raman is also an additional technique which is being very widely used now to study materials under shock compression. About the experiments were by Institute of Shock Physics, and then other reflection and etc. etc. So just remember, I'll try to add here one additional measurement, the Raman measurement. In recent years, it has been possible to couple shock wave physics with studies at synchrotrons, and Here are a few representative papers which reflect the kind of measurements which are possible now. One set of experiments are being done at the beamline called matter extreme conditions at LINAC Coherent Light Source, which is a free electron laser in Stanford. This is basically laser shock studies. Several other ways to generate Shockwave physics were integrated into a dynamic compression sector at Advanced Photon Source in US. Here is a reference which gives you some details about, and this is more for laser shock. So this is for impact stresses that you can do the experiments with a gas gun and then do the XRD, and or otherwise do it with the lasers and do XRD. These are at the dynamic compression sector, APS. Again, the last few years, a couple of years, additional developments have taken place at DCS and APS, as well as at ESRF, where people are now trying to measure the X-axis, X-ray absorption time structure, to deduce information about the coordination change as a function of pressure, as a function of shock compression. Let me quickly, before I conclude, show here an example of silicon under shock compression. Silicon undergoes a large number of phase transformation. Its initial structure is a cubic diamond phase. And as under static pressure, it goes to a detergent phase, and then to an orthorhombic IMMF phase, and to a simple hexagonal or primitive hexagonal phase, which then to orthorhombic, HCP, FCP, and so on at various places. The continuum measurements could detect only the phase changes which had the large volume. Specifically, it could give a suggestion that there will be this phase transformation which had about 20% water change. Possibility of shock melting, though it has been recognized by continuum measurements, but it has not been detected could not be detected definitely by the continuum measurements. Only indirect conclusions could be deduced through the sound speed discontinuities, basically because once material melts, it does not have shear strength, so the bulk sound speed really falls down. So on those kind of deductions, one could kind of state that silicon melts under shock compression. However, there's no explicit confirmation of that. So we investigated silicon along the Hugoniot in the stress range from 26 to 54 GPa using XRD. And at 26 GPa, it was confirmed to exist into primitive hexagonal phase. Okay. We also studied what one calls as off Hugoniot states. And what turned out was that along once the Hugoniot, if it is gone into a liquid phase, if you shock it for a little more stress, it crystallizes. And the crystalline features are representative of what phase diagram would suggest at that particular. Here is the nature of experiments which were done. There is an impactor, which makes this is silicon, which is a single crystal silicon oriented along 100. Is backed up by lithium fluoride. At this interface, gold is deposited, which acts as a reflector for velocity interferometer. It's at visor. And when the shock is launched into this and is traveling, let us say, some distance into silicon, the X-ray pulse is launched into this, and the deflection is recorded at various pressure. You see here typical particle velocity curves recorded in these experiments. For example, this is elastic jump, and then there is an inelastic, and then this is the phase change indication, which is taken at finally study value, takes representative of activity and stress it adapts. These are the X-ray diffraction images which are recorded. This one is, for example, close to 30 GPa. The sharp dots are incidentally from lithium fluoride single crystal. And you can see the partial rings are representative of textured phase of silicon and can be identified as 001 of primitive hexagonal or simple hexagonal. This is 101 or simple hexagonal. So at a higher stress, at something like close to 35 GPa, all these other peaks vanish and you have a broad hump. This again is because of certain single crystal features of lithium fluoride or leftover unshocked silicon. So one can show here explicitly through the loss of several X-ray diffraction peaks that the material has actually molten. In fact, it cannot necessarily be stated that it is molten. It could be that it is gonomorphous, but one can, through careful interpretation in terms of the known melting curve, etc., one can deduce that it is indeed, one can conclude that it is indeed molten. Here are some of the one-dimensional curves which were deduced from here. Unlike simple X-ray diffraction experiments under static pressure and shock compression, one has to calculate back the profile because there are lots of other components into this, and the geometry is a little unusual. So we calculated the diffraction patterns and compared it with the observed ones. At somewhere close to 30 GPa, the pattern is essentially of primitive hexagonal phase. At slightly higher pressure, you start seeing this broadening, little broadening. This is an indication that melting is beginning to take place. At still higher pressure, this has become much broader. And so you can see there's a larger amount of melting. At still higher pressures, in fact, only this molten phase exists. Recall that sometime back we talked about the interaction of shock waves with various interfaces. This has a less impedance than this. As the shock travels into this bounces back but reflects another shock into this. So therefore, if initial stress was or uniaxial stress was longitudinal stress was let us say some value, after reflection it will be more. So this we call as reshock. For example, if we shock this initially to 30.5 GPa, this example, then after reshock from lithium fluoride, the silicon was taken to 35.8 GPa. And if you analyze the diffraction pattern, then it is a combination of liquid phase, a small component of primitive hexagonal phase, and hexagonal closed back phase, which was expected at much higher stresses and the static pressures. And it had not been earlier observed ever in any of the shock experiments. So you can see that the reshocking, that it took it to the molten phase and then it brought it back into a crystalline phase, which was representative of the higher compressed state of silica. I will skip more details because of the shortage of time. I will refer to this article that we wrote on this, but quickly mention that the various states deduced from XRD are confirmed with the static results. Okay, so this is, for example, the present continuum curve from the WISER data that we could, which is comparing well with the static data. These are the ones from the XRD primitive hexagonal phase. And see here, and it's again matching with the static data. This is after reshock that we get these data points, and this is matching well with the hexagonal closed stack phase data, which is known. Based on what we got, we could construct a phase diagram of silicon. Yes, so these are kind of reshock state. We initially had this state, and after reshock, it went into this state. So when it went into this state, or at here, it could go into a crystalline phase, but at much higher stresses, it didn't. So it stayed liquid. So various other conclusions could be deduced, and I'll skip this to take details here. In case one is interested in more details, I'll be very happy to discuss at a later time, either in later talk or at personal level. I guess I'll stop here. And the next lecture, what we will cover is several more measurements, which are representative of the kind of the shock studies which are presently being done at international level. Thank you very much.